Okay, we continue to learn about Chapter 1, matrices and systems of equations. Section 3, matrix algebra. Now we consider Part 2, matrix addition, scalar multiplication, matrix multiplication, and the linear system. Now we consider about matrix addition. Two matrices with the same dimension can be added by adding their corresponding entries. So if A with representative entry small a subscript ij and b equals bij are both n by n matrices, then the sum A plus B is also an n by n matrix, where the ij entry is aij plus bij for each ordered pair ij. Here we have two simple examples. So the first one is two by three matrices. We compute its matrix addition. So it is also a 2 by 3 matrix, right? And the first row should be 5, 4, 3. And the second row should be 5, 7, 9. Okay, and now we consider the following simple example. Here is a 2 by 2 matrix with entries first row 2, 4, second row 3, 1, minus also a 2 by 2 matrix. The first row 4, 5, the second row 2, 3. And we will also get a 2 by 2 matrix for the matrix addition. And the 2 by 2 matrix, the first row entry should be minus 2, minus 1. The second row entry should be 1, minus 2. For matrix addition, we have some special concept. So the first one, additive identity. The zero matrix, that is an n by n matrix, whose entries are all zero, we call it additive identity. So we know that A plus this zero matrix equals this zero matrix plus this matrix equals this matrix itself. We can just obtain this by definition of a matrix addition. And secondly, we also have additive inverse. So what is additive inverse? Each n by n matrix A has an additive inverse. The additive inverse, in fact, is minus 1 times A. So we know that A plus minus 1 times A equals the zero matrix, the additive identity matrix, which equals minus 1 times A plus A. And later, for simplicity, we just denote the additive inverse of the matrix by minus A. Now we consider another computation called scalar multiplication. If A is an n by n matrix and alpha is a scalar, then alpha times A is a matrix whose ij entry is alpha times aij. So here we see an example. Here A is a 2 by 3 matrix, and then we know that 3 times A is also a 2 by 3 matrix. The first row should be 3 times 4, 8, 2 sequentially. So it's 12, 24, and 6. And the second row, we also use 3 times each entry. So we will get 18, 24, and 30. Okay, this is the scalar multiplication. And now we will introduce another operation on the matrix. So it's matrix multiplication. And the matrix multiplication relates closely to the linear system. We will see later. A system of one linear equation in one unknown we can write as ax equals b. Here, a and x and b, they are all scalars, or they are 1 by 1 matrices. You can also consider like this. Generalization: if x is not only one variable, it's a vector, and then the small a is not only a scalar if it's an n by n matrix, and similarly the b is not a scalar, it's a vector, then we will consider a general linear system, n by n system. So we consider ax equals b. Here a is an n by n matrix, and x is an unknown vector in n-dimensional real vector space, and b is also a given vector in Rn, m-dimensional vector. So in general, for linear system, n by n linear system, the first equation is A11x1 plus A12x2 plus TL plus A1nxn equals B1. The second equation is A21x1 plus A22x2 plus TL plus A2nxn equals B2. And the mth equation is am1x1 plus am2x2 plus TL plus amnxn equals bm. And as we introduce the matrix, the vector, so we can write this system as the left side, A times X. So if we write like this, the matrix A times X, for this purpose, we need to define the matrix multiplication. So in order to express the linear system, we would like to define A times X as the first entry will be A11x1 plus A12x2 plus TL plus A1nxn, right? So we need this. And for the second row, A times X will get the left side of the second equation. So should be A21 times x1 plus A22 times x2 plus TL plus A2n times xn. Similarly, for the mth row, we want the entry to be am1x1 plus am2x2 plus TL plus amnxn. Right? So we define matrix multiplication just for the purpose of expressing the linear system. So for the simple case, for a linear equation with n variables, so now we have only one equation, it's a1x1 plus a2x2 plus TL plus anxn. So this one equals b. And here, this is a simple case, right? And for the matrix A, we can write as it composed by column vectors. The first column for A, the second column for A till the nth column for A. And then A times X, we can also write as x1 times a1 plus x2 times a2 plus TL plus xn times an. To be careful that here, x1, x2, TL, xn, they are scalars in R1, right? They are scalars, where a1 here, a2 here, TL, an here, they are column vectors. So we can write A times X, the left side of the linear system, to be the linear, right? The linear combination of A1, A2, TL, an. So here for each term, x1 times the first column for A, this is a scalar product. Right? And also x2 times a2 TL xn times an, this is also scalar product. In order to determine the ith entry of ax, we use the ith row of A. See, we have an arrow here, so this is the ith row of A. So AI times X, which equals just AI1, this scalar, times X1, also scalar here, plus AI2 times X2 plus TL plus AIN times XN. So this one is the ith entry of A times X. This is a matrix multiplication, right? The ith row of A times the column vector of X. For each row, you do this operation. Right? For each row, you do this row times this column vector. You will get eventually A times X. And A times X just equals B, where B composed by B1, B2 till Bn. Okay. So this is a special case of matrix multiplication, which is derived from the linear system. And now we give an important concept of linear algebra, which is linear combination of vectors. So its definition is like if A1, A2 till An are vectors in Rm, and C1, C2 till Cn are scalars, then a sum of this form C1A1 plus C2A2 plus TL plus CNAN is said to be a linear combination of the vectors A1, A2 TL An. So first we give vectors, right? M-dimensional vectors A1, A2 TL Am. You can just consider as the nth column of M by N matrix A. So you do this linear combination here, C1, C2, Cn, just scalars. Okay. And we can consider also the geometric interpretation of a linear combination of vectors. Say, if A1, this is m-dimensional vector, this is a vector, you can draw a line on the plane if it's two-dimensional, okay? And a scalar C1 times A1 means if C1 greater than 1, then means you stretch this line, make it longer. Or if it's greater than 0, smaller than 1, means you compress this line, make it shorter. Or if C1 is negative, then this means you choose the opposite direction, right? So this is for the scalar multiplication. And then if you do this summation, it's like you choose a new vector, the direction, maybe between A1 and A2. For example, C1, A1 plus C2, A2. You just choose one vector. The direction is determined by this summation, maybe between these two directions, A1 and A2. Okay, this is the geometrical interpretation of linear combination of vectors. Then you can see the product A times X is just a linear combination of the column vectors of A. So this is important. Later we often use this expression. So A times X just equals X1 times the first column of A plus X2 times the second column of A plus till plus Xn. This scalar times the nth column of A. Okay. Now, we give the consistency theorem for linear systems. This theorem said that a linear system, Ax equals b, is consistent, is solvable, if and only if b, the right-hand side vector b, can be written as a linear combination of the column vectors of A. So why we see like this? Because Ax can just be written as x1 times the first column of A plus x2 times the second column of A plus till plus xn times the nth column of A, right? So if the column B can be written as a linear combination of the column vectors of A, then the scalars are just coincide to the solutions of the linear system, right? See this simple example, x1 plus 2x2 equals 1, 2x1 plus 4x2 equals 1. Just from this expression, we can see that this linear system is inconsistent. Why we can see like this? So the reason is that you see the left side of this system is equivalent to x1, this scalar, times a column vector 1, 2, plus x2, this scalar, times a column vector 2, 4. See? So this is a linear combination of vectors. One is 1, 2, another one is 2, 4. They are in the same direction. This means the second component must be 2 times the first component. So any x1, x2, you choose it. You will get a vector. The second component is 2 times the first component. However, the right-hand side vector is 1, 1. So it is impossible, right? You cannot find x1, x2 such that the combination is like 1, 1. So this system is inconsistent. So this is what we use for consistency theorem for linear systems. And now we give the general definition for the matrix multiplication. It is possible to multiply a matrix A times a matrix B if the number of columns of A equals the number of rows of B. So we define AB like here. A times B equals AB1 for the first column, AB2 for the second column till ABR for the rth column. Here, B is an n by r matrix. Here, A is an n by n matrix. So if A is n by n matrix and B is n by r matrix, then the product AB equals a new matrix C with representative entry Cij is an n by r matrix whose entries are defined in this way. So Cij just equals the ith row of A times the column vector Bj. See? So the first subscript I means the ith row for the first matrix, and the second subscript J means the jth column of the second matrix. Okay, so eventually Cij equals the summation of Aik times Bkj, where k varies from 1 to n. So from this notation, you will also know that y, when do a matrix multiplication, the number of columns of A, the number of the column of the first matrix must equal the number of rows of B, the number of rows of the second matrix B. Okay. Now we can consider also this figure to see what is matrix multiplication. So matrix multiplication, you can get C matrix here. So if A is an m by n matrix, B here is an n by r matrix, then the new matrix C, which equals A times B, is an n by r matrix. The entry Cij just equals the ith row times the jth column of B, ith row of A times the jth column of B, and you will get Cij. Okay, so Cij just equals AI1 times B1j plus TL plus AIK times BKJ plus TL plus AIN times BNJ. Okay, here we want to emphasize that the multiplication of matrices is not commutative. Okay, so if A is an n by n matrix and B is an n by r matrix, where r does not equal to n, then what is about AB, the dimension for the matrix AB? The dimension is n by r, right? The number of rows of A times B equals the number of rows of matrix A, and the number of columns of AB equals the number of columns of B. Okay. And how about BA, B times A? If we write B first, then BA, can we do this multiplication? Because B is an n by r matrix, where A is an n by n matrix. Then because r does not equal to n, so you cannot do this matrix multiplication. We can't do this. Okay. And another case, if A is an n by n matrix and B is an n by n matrix, where m does not equal to n, then what is A times B? What is B times A? We know that you can multiply A and B, right? Because A times B should be an m by n matrix, is a square matrix. And how about BA? BA, because B is n by m matrix and A is n by n matrix. So you use B times A, you will get an n by n matrix. Because m does not equal to n, so this means the dimension of these two multiplications are not the same. Of course, you cannot write AB equals BA. So the matrix multiplication is not commutative. And also, even if A and B, they are both n by n matrices, in this case, you will calculate AB and BA. They are both n by n matrices. However, in general, you can also counterwrite AB equals BA. In general, AB does not equal to BA. So we say simple examples. So this A times B, the matrix A is a 3 by 3 matrix. Okay, and the matrix B, this matrix is a 2 by 3 matrix. Can we do the multiplication? We can't, right? Because the number of columns of the first matrix is 3, while the number of rows of the second matrix is 2. You can't do the multiplication, matrix multiplication. And how about the second one? We change the position of the first and second matrices here. So we get this one times this one. So the number of columns for the first matrix now is 3, while the number of rows of the second matrix is also 3. So now you can do the matrix multiplication. See? So for matrices, you should keep in mind that in general, this matrix multiplication is not commutative. Okay. We introduce the notational rules for such simple operations on matrix. We first have these rules. Both scalar and matrix multiplications are carried out before additions. So this is very easy to follow, right? When you face also scalar multiplication, matrix multiplication, and the addition, matrix addition, then do the multiplication first. Later do the addition operation, okay? So here, a simple example, A, B, C here, and if I want you to do A plus B times C, so you first do this multiplication, matrix multiplication, the B times C. So B times C, the 1 entry should be at the first row of B times the first column of C, for example. So you will get 1 times minus 2 plus 3 plus, times 3. So it should be 9 minus 2, 7, right? So you get 7, 1 entry 7 here. So after you do this matrix multiplication, you do a summation, and you will get this result. Okay, and if you compute 3a plus b, so you also do the scalar multiplication first, you will get this one. 3 times a, this means for each entry of a, you use 3 times this entry, you will get this 3 times a. And then plus b, you will get this new matrix, 2 by 2 matrix. Okay,